Okay, so we are starting on number 13. That's where we left off. 13 is where we get into chapter 3 stuff. Okay, because now we're going to be talking about exponential functions, which is what chapter 3 was about. And this is the doctors who prescribe a certain medicine. So we have P of t represents the probability that they are prescribing a specific medicine, and it follows this equation that's exponential because you have e to the negative 0.25t, where your variable is up in the exponent and your base is a constant. That's what makes this an exponential equation. Okay, well first, and then it says, let's see, other information, t is time in months. And what else? And then P represents the percentage of doctors. Percentage of doctors. Well, part A is just asking, find P1 and P6. All I'm doing there is I'm just plugging 1 in for T, plugging 6 in for T. Okay, pretty straightforward. Any questions about that? Right. So I think in my case, I get 21, or about 21. I think there's some rounding there, but I get about 21 and about 75 for P of 6. Notice I'm rounding to the nearest whole number. It tells me to do that in the problem. And what do these actually represent? They're percentages, right? This represents that 21% of doctors are prescribing this medication after 1 month, and 75% of doctors are prescribing this after 6 months. Okay, very nice. So that's part A. Pretty straightforward. Part B is calculate the derivative. That's my derivative here. So there's a couple different ways I can go about this. First off, if I want to make this a little bit easier on myself, I could distribute this 100. So I could distribute that 100 to both terms and then take the derivative. But we also know that if you multiply something by a constant, that doesn't affect the derivative. So I could also just take the derivative of this piece and then multiply my answer by 100. Everybody okay with that? That's another option. I could just take the derivative of this, and then when I'm done, multiply it by 100. So let's take the derivative of that. What's the derivative of 1? 0. Okay, so I get 0 minus, how do I take the derivative of exponential functions? Specifically E functions?
1.
No. Natural log is the inverse of an exponential function, but it's not my derivative. Riley?
Multiply the constant in front of the e by the constant in the exponent, and then leave everything else the same?
Right, leave everything the same, but then multiply by whatever constant's up there in the exponent. So I'm going to multiply this by negative 0.25, and then leave everything else the exact same. Do we see that? So there's my constant that was up there in the exponent. Okay, and that's being multiplied. So if I simplify this a little bit, I get 100. The 0, I don't need the 0 anymore. What happens with these negatives? These negatives become positive, and I'm left with 100 times 0.25 e to the negative 0.25 t. Well, 100 times 0.25, what's 25% of 100? That's just 25. And there's my derivative. Okay, any questions about that? So just as a reminder, right? If you have e to the kt and you take the derivative, your derivative is you just bring down that constant and leave everything else the same. Notice you don't bring down the variable with it, just the constant. You just bring down the constant. Okay, very nice. Part C. When will 90% of doctors prescribe this medication? How does this problem work?
Solve for t.
Right, we're solving for t. We're solving for a month value. Exactly. So we're going to be solving for t. What do we do with that 90?
Plug it in for the probability.
Plug it in for p. Now, where? Do I plug it into the derivative or plug it into my original equation?
Original.
It's a little tricky because we just calculated the derivative, but we're not actually using the derivative for this part of the equation. In fact, we don't actually use the derivative for anything else. It's just gives practice doing derivatives with exponential equations. So with this, I'm just plugging 90 in to the original equation. Everybody okay with that? So solve for it, right? You can divide both sides by 100. You're left with 0.9 equals 1 minus e to the negative 0.25t. I'll subtract both sides by 1, divide by a negative, and you're left with 0.1 equals positive e to the negative 0.25t. How do I get past this point? Right, like Abigail was talking about, logarithms are my inverse function. So if I ever want to get rid of an e function, I can just take the natural log of both sides. So that gives me natural log of 0.1 equals, natural log of e is going to cancel out, and I'm just left with what's up in the exponent. Okay, so how did I do that? I'm just taking the natural log of both sides. And then I can just divide by negative 0.25, and I get t is equal to natural log of 0.1 over negative 0.25, which is about 10 months. Squiggly, 10 months. So it only takes about 10 months before 90% of doctors are prescribing. Okay. Part D. Part D asks the question, what's going to happen if I let time get infinitely large? What's going to eventually happen?
The heat death of the universe?
Yes. Besides that, what do we expect to happen with this medication over the course of a long period of time?
Well, I mean, the exponent will go towards 0.
Yeah, right. So if I take the limit as t approaches infinity of this equation, right? We're letting t get really, really large. I can't remember how it words it, but it's something like, anyway, but it's this idea of we're letting t just go off, right, till right at the end of time. Let's see, e to the negative 0.25t. Well, if we let t get infinitely large, what's happening to this exponent? This exponent is becoming infinitely negative. So I end up with this. Everybody okay with that? Even if I'm multiplying it by 0.25, a quarter of infinity is still infinity. So we end up with e to the negative infinity. Well, what's true about this term right here? Right. Since this is a decay function, since I have a negative exponent, this is a decay function, and as my function goes off to infinity for a decay function, it's slowly approaching 0. So that just goes to 0, and I'm left with 100 times 1 minus 0, which is just 1. So if we let time go on, what will eventually happen? 100% of doctors are going to be prescribing this medication.
That last doctor waiting for the universe.
That's right. That one last doctor waiting for the heat death of the universe. Okay, awesome. So that is question number 13. Question number 14. Moving on, unless there's any questions about that one. Okay. This one's another nice simple example of exponential functions. This one's specifically compounded interest, simple interest here. So we have the question is, how much money must you invest now at 4.6% in order to have $10,000 after 4 years. Oh, right, that's I'm getting this mixed up again. To have $10,000 after 5 years. Sorry, 5 years. How much must you invest now? So what type of question is this then? What is it really asking? I want $10,000 after 5 years. How much should I invest now? What is this talking about?
How much do you need now? Present
Yeah,
value?
present value. That's the word we use for it. This is talking about present value. It's asking for present value because this right here is future value. We want a future value of 10,000 and we're looking for the present value. So remember, there's a couple different ways we can set this up. Somebody help me set it up one way. How could we set it up? What's a possible way we can set this up?
We could create an exponential with
Right, create an exponential equation. So I'm going to have e to the 0.046 t. What's t?
5.
I have a t value, right? Times 5.
and then we solve for the, like, we set it equal to
Oh.
10,000.
I can then set it equal to 10,000 and solve for what? Principal, where do I put that? Before the e, right? I like to use P naught for principal because it's like your initial amount that you're starting with. So this is one way I could do it. This is me just solving for P naught using my exponential rules and using my normal future value setup to do this. Let me just put this on the other side to give myself some more room. But remember, we had another way that we can calculate present value. I like this way because it makes logical sense. We want it to end up equaling 10,000. I like having future value on the other side of the equal sign. But remember, we had a different way we could do this. If I want present value, I can actually make a normal exponential function with my future value as my starting amount. As long as I do what?
Make it negative.
Right. As long as I make the interest negative. Because by doing that, all I'm doing is I'm saying, let's move backwards. Let's go backwards in time. Let's start with 10,000 and then go backwards in time 5 years to see where we're at.
Maybe you just have a really
So, yeah. So in my case, either way, you should get about $7,945.34. Make sure with all these problems you're paying attention to what you're supposed to round to. Okay, this one says round to the nearest cent. So that's 2 decimal places. Okay. Awesome. Questions about this one? Okay, moving on. Question number 15, another good exponential problem. This is an office machine that's depreciating in value as time goes along, right? This happens to a lot of different products. As time goes along, the value of that product declines. So this product, the office machine, is purchased for $9,200. What is that going to represent? Your P naught, right? Your initial value. So I'm going to go ahead and put P naught is equal to 9,200. Okay. And then under certain assumptions, its salvage value V is in dollars, is depreciated according to a method called double declining balance by basically 66% each year, giving you an equation, or sorry, that one's 66, this one's 79% each year. So really, this problem helps you out by just giving you the equation. So it gives me 9,200 times 0.79 raised to the t power. Okay. All this one's asking for is find v prime of t. And then tell me what that actually means. So this is just a good reminder of how does this derivative formula work. This isn't going to be quite the same because I'm not working with my normal e base. Normally I have e to the x, e to the t, but now I have 0.79 to the t. Is this still an exponential equation? Yes, it's still exponential because your variable is in the exponent and your base is constant. So this is still exponential. What's my formula for an exponential equation like this? What's my derivative formula? Sorry, what's my derivative formula for an exponential equation like this?
Power rule?
No, not the power rule, because this is not a power function. Rylan?
A natural log of the base times the original function.
Right. So, first of all, what do I do with this 9,200? Keep it there. Right, that 9,200 is going to stay there. And then when I take the derivative of this piece, right, you keep the same thing, just like with my base e, where when you take the derivative of like an e to the x function, it stays the exact same. The same thing's going to happen here. It's going to stay the exact same. I'm still going to have 0.79 to the t, but then I'm going to multiply it by the natural log of whatever the base is, natural log of 0.79. Very nice. So there's my derivative. There's my derivative. Awesome. And then if you want, you can multiply a natural log of 0.79 and 9,200 together. What does this represent? What is this kind of...
This is the amount it depreciates at a certain time.
Yeah, there's a very important word that I'd like to hear. The
rate of change.
rate. Exactly right. It's the rate of change that it's depreciating. So you're absolutely right. It deals with how it's depreciating, specifically the rate at which it depreciates. Okay. So what should this... We don't actually see this because we haven't actually plugged anything into my calculator. But what should be true about this derivative? What should be true about this derivative? If this office machine is depreciating in value, it should be negative, right? Which it actually is. We don't see it because we haven't actually calculated this, but this is going to be a negative value right there. Natural log of 0.79 is negative. So sure enough, your derivative ends up being negative because it's losing value. Very nice. Okay. So V prime represents the rate of change in the value of the machine. How is the value changing each year? Or you can also think about it as per year. Okay, awesome. Okay, moving on. Once again, feel free to stop me. Just whenever, if you have any questions. Feel free to stop me. Okay, next we have an integral. Okay, we've been doing lots of this. This review is chock full of good applied problems, but this is another one where we get to just take a break from that and just focus on the straight math here. Okay, how would I do this integral of -2 over the 6th root of x to the 5th?
I would try to make it digestible.
Yeah, let's make it more digestible. Let's rewrite this. That's the key to this problem, is if I look at this the way it is now, we might get overwhelmed of like, how the heck am I supposed to do this? Let's just rewrite it. Rewrite it in a form that's more digestible. Well, first of all, what can I do with the constant? What can I do with -2? Pull it out of your integral. It's a constant. So I can pull that out of the integral. So that leaves me with -2 times the integral of... How can I rewrite this?
X to the 6th to the -1/6.
Okay, so first of all, it's in the denominator, which means I can write this with a negative exponent, right? And anytime you see roots, how do roots work with exponents? And it creates fraction exponents, right? So any root you see is going to go in the denominator of my exponent. So this leaves me with x to the negative. Why is it negative? Because it was in the denominator. And then because it's the 6th root, you're going to have a 6 in your denominator of your fraction. What goes in the numerator?
Oh, the internal.
Yeah. The internal power, if it's being raised to a power, that goes in the numerator. So in our case, it's x to the negative 5/6. Okay, much nicer, much more digestible. Do I have an antiderivative rule for a function like this? I do. I have an antiderivative rule for this. So now I can use that antiderivative rule. I keep the -2, and then I'm going to use my antiderivative rule, which is just you add 1 to the exponent and then divide by that new exponent. Okay, so I get -2 times x to the negative 5/6 plus 1 is just 1/6 divided by 1/6. How do you divide by fractions? Flip and multiply. So this leaves me with -12 x to the 1/6. I'm missing something. Plus c. If you don't include that plus c, it's going to mark you completely wrong. Even though you did everything else right, it's going to mark you completely wrong if you don't have that plus c. This is why I'm having you show your work and have that worked, and that work's going to be submitted to me so that I can give you points in case you miss it by missing the plus c. Just be careful with that. How do I know that I need the plus c?
Because you have an
We don't have constraints.
It's right, there's no bounds. This is an indefinite integral. So if there's no bounds, you need to make sure and have a plus c at the end. Okay, very nice. Yeah, Aiden.
So I followed along, but I'm just confused on why you put it, like why it's over each other. Like, if you go back like 2 steps to where, I'm assuming you used the x to the n dx and then it equals the 1 over the n plus 1, like where you
Yeah, so it doesn't matter because if you wrote it like this, 1 over negative 5/6 plus 1 times x to the negative 5/6 plus 1, this is multiplication, right? But if I wanted to, I could go ahead and multiply these two things together by just putting the other one over 1.
Oh, okay.
And by multiplying those two things together, you have 1 times x, right? You multiply the top 2 numbers, which just leaves you with this, and you multiply the bottom 2 numbers, which just leaves you with that. So that's just me combining it into one fraction.
Okay.
Okay, 17. So as you can tell, we're on to chapter 4, which was all about integration. 17 is you got a particle moving along, okay, and the velocity of the particle is given by negative 0.6 t squared plus 12t. Notice I'm using v for velocity. And now I want the distance for the first 6 seconds. How far does the particle travel after 6 seconds? Oh, what would the derivative give me? That would give you acceleration, right? If you take the derivative of velocity, it gives you acceleration. We don't want to take the derivative. We want to take the antiderivative because the antiderivative will tell me about position, and that's what it's asking. Remember, if you have a rate function, then the integral of a rate function gives you total change, right? So integral of a rate function will give you total change. So in our case, since it's asking for distance, we want to take the integral of this function in order to get it in terms of distance. Because, like we talked about before, velocity is the derivative of distance. So to go backwards, I have to take the antiderivative. What are my bounds? Or do I have bounds?
Oh wait, no, it'd be 0.
0 to 6. I want the total change over those first 6 seconds. So I'm gonna integrate this from 0 to 6. 0 seconds to 6 seconds. Okay. Very nice. Okay. I'll go ahead and how do I do this? I use the fundamental theorem of calculus. So I'm going to take the antiderivative and then plug in my bounds. What's my antiderivative here? I get negative 0.6 times t cubed over 3 plus 12 times t squared over 2. And I still need to evaluate that from 0 to 6. I'll simplify this a little bit. Negative 0.6 over 3 is just negative 0.2 t cubed plus 12 over 2 is 6 t squared. Evaluate that from 0 to 6. What happens when let's see, if I plug in 6, I get 172.8. When I plug in 0? 0. So I get 172.8 meters. I think this is in meters per second. Okay. Yeah, yes. Questions? Any questions? So the next part, so this was part A. Part B is, how far does it travel during the second 6 seconds? Well, how does that change my problem?
No, you're.
Right, it just changes your bounds. So for part B, you're just integrating from 6 to 12. But you're doing the exact same integration, which is nice because I don't have to do all the work for the antiderivative again. I can just skip right to this step, negative 0.2 t cubed plus 6t squared, because that's the antiderivative. But now my lower bound is 6 and my upper bound is 12. I need to plug in 12 and plug in 6. Let's see what I get. Which in our case is when I plug in 12, I get 518.4. When I plug in 6, what do I get? Yeah, we already did the work for that. 172.8. Subtract those things, and I get 345.6 meters. Picking up speed. It's going farther and farther. Cool. Questions about this one? Questions about number 17? This is distance for the second. 6 seconds. Cool. 18. Another just basic integration where we're not going to worry about an applied example. This is the integral of x to the 5th. 1 minus x to the 6th raised to the 7th. Okay. Another indefinite integral. So do you need to worry about the plus c? Yes. No bounds. Anytime you don't have bounds, you need to make sure and put a plus c at the end. Notice how in this last problem, I had bounds, so there was no plus c. I didn't have to worry about putting a plus c with my integral. Okay, how does this one work?
Can you scroll up a little bit?
Sorry. Like this?
Yeah.
So just you can catch up. Okay. How is this one going to work?
We need to use the inverse of the. We need
Yeah.
the integration formula of
The opposite of the chain rule, right? Is that what you were saying? I'm sure it was. Yeah. So I need to use my integration method that was kind of the opposite of how the chain rule worked. Why? What do we notice with this problem?
It has a function within a function.
I have a function inside of another function. I have 1 minus x to the 6th inside of this raised to the 7th power. So what we had a name for this integration method. What was it called?
Integration by parts.
No, integration by parts is if we had two functions being multiplied by each other.
Substitution.
This is integration by substitution. You'll notice there's no example problems for integration by parts because it's not on the test. So you don't have to worry about you won't have to worry about integration by parts on the test. But you might see integration by substitution. So what am I substituting? How does substitution work again? I create a temporary function u that's going to equal whatever that inside function was. Right. So 1 minus x to the 6th. So in our case, I'm going to let u equal 1 minus x to the 6th. Everybody okay with that? Okay. What do I do? Now what do I do? Not yet. Oh, sorry. Because I'm missing a very important piece. I'm missing this dx. In order to integrate it in terms of u, I also have to switch the dx. I have to switch the dx in terms of du. So in order to be able to do that, what do I have to do?
Find the antiderivative of u.
Not the antiderivative, the derivative. Why? Because when I find the derivative, right, this is my notation for a derivative, du over dx. And by doing that, you can solve for dx. I get dx is equal to du over negative 6x to the fifth. Everybody okay with that? That's why we take the derivative of whatever your substitution is. So with integration by substitution, you figure out what you want to substitute, and then you take the derivative of that so that you can substitute your dx as well. Okay. If we did it right, let's see, we're going to have x to the fifth up here. We're going to have, instead of 1 minus x to the sixth, what can I use there instead? Just a u. I'm going to have u to the seventh power. And then dx is this du times negative 6x to the fifth. If we did it right, what should happen?
It will cancel out the x.
The x's will cancel out. I have an x to the fifth in the denominator, and I have an x to the fifth in the numerator. Those will divide to just equal 1, which means they're just canceling out. The negative 6 doesn't cancel out, though. Where can I put that negative 6? Outside. I can put it outside the integral because it's just a constant. But just be careful when I do that. It is in the denominator. Everybody okay with that? So keep it in the denominator. Okay, and that leaves me with 1 over u to the 7th du. Do I know the antiderivative formula for 1 over u to the 7th? Yeah. Remember, I can just rewrite 1 over u to the 7th as what? U to the negative 7. And now I'm just using the antiderivative rule the power rule for antiderivative. Okay, so this leaves me with 1 over negative 6 times, my antiderivative of that is I'm going to add 1 to the top, so that gives me negative 6, and then I'm going to divide by that new number. Okay. Very nice. Oopsies. Oh, sorry. I put a du there. I don't need that du because I'm done. I've taken the antiderivative, right? The antiderivative is there, or is done. Instead of putting a du, what should I put? Plus c. Yeah, very nice. Okay, simplify this. Negative 6 times negative 6 gives me positive 36. U to the negative 6 plus c. Can I call it good there? No. If you put it in like this, you're going to get the answer wrong. In order to finish, I have to put it all back in terms of x. So, what is u equal to? 1 minus x to the 6th. Awesome. Any questions about that one?
Could you just do 1 minus x to the 6th to the negative 6 over 36 plus c?
Yeah. Mm-hmm.
Okay.
Yeah, you can combine that into one fraction if you want. You can also, since it's to the negative 6, you could also move that to the denominator and put it as a positive exponent. You could have 1 over 36 times 1 minus, right? So I could rewrite it like this. 1 over 36 times 1 minus x to the 6th raised to the 6th. Right? You could also rewrite it like that because that's what a negative exponent means. Once again, with the functions, they're not very picky about how you simplify them.
Okay.
So, which is nice. Yeah. Hey.
I'm confused on where you so I'm on the second step down,
Uh-huh.
and then we put it over to the other side, and then now we're about to multiply it.
Uh-huh.
Why did you put the negative 6 under the u?
It's the same thing. It's the same thing where I could have written it like this, 1 over negative 6 times u to the negative 6. But if I wanted to just, and then there's still this other 1 over 6, right? So this is where this is my antiderivative. right? I could have written it like this, but instead I just made it one single fraction by doing u to the -6 over -6. Okay.
Oh, I'm supposed to be basing it off one of the antiderivative rules, right?
Yeah, because this is my antiderivative rule for something like this.
Okay.
You do
Which
that example.
antiderivative rule were you like?
It's the, because when we use, is if you look at that one, x to the n, that antiderivative rule, this antiderivative rule still applies even if you switch to u. If you change the variable to u, it's still the same type of function, so you still use the same derivative rule.
Okay, so we're still using that same rule.
Yeah, still using that same rule. Cool. Okay. I think we're on 19. Number 19. Now we're into chapter 5. Number 19 is consumer and producer surplus. Okay. So, where is it? There it is. Okay. It gives me a demand function. X minus 4 squared. It gives me a supply function of x squared plus 2x plus 6. And then it asks me three things. If you remember, these consumer and producer surplus problems were all the exact same. Find the equilibrium point, calculate the consumer surplus at the equilibrium point, and calculate the producer surplus at the equilibrium point. How do I find the equilibrium point? Set them equal to each other, right. So I'm going to just set these equal to each other. So for A, the equilibrium point is just, I'm going to set these two things equal to each other. Okay. Well, in order for me to solve this, what am I going to have to do with that left side? I'm going to have to distribute and multiply that out. Okay. So I get x squared minus 8x plus 16 equals x squared plus 2x plus 6. Now I can subtract things over to get it all into one side. Okay. So I'll go ahead and subtract x squared, subtract x squared. What do you notice? Both sides cancel, so both of those will go away. And then, at this point, I can kind of pick and choose where I put things. Since I was able to get rid of the x squared terms, I can pick and choose where I put it. So I'm going to add 8x and add 8x. And then I'll subtract 6 and subtract 6. Okay, that leaves me with 0 over here for my x terms, but I'll have 10. And then over here, that leaves me 0 there, and 2x plus 8x equals 10x. What does x equal to? 1. Woohoo! Okay. So, the equilibrium point is producing only one unit. Maybe this is in terms of thousands of units. I don't know. But we just produced one unit at what price?
We plug that into d of x.
Or s of x. Doesn't matter which one, because that's the whole idea of equilibrium point, is the values are going to be the same for both of them. So I can plug them into either of them. So I can plug that into my demand function, and I get 1 minus 4 squared, which is negative 3 squared, which is 9. Or you can plug it into your supply equation. And guess what? You're going to get the same thing. 1 squared is 1. 2 times 1 is 2. Plus 6. Yep, sure enough, you get the same thing. So there's my ordered pair. I should sell 1 unit. What's the 9 represent?
1 unit at $9.
Yeah, your price. So I should sell 1 unit at $9 in order to optimize my consumer surplus and producer surplus. Yeah. Perfect. Part B. Now let's actually find my surpluses. Part B is, I think, consumer surplus. And for these, remember, you'll have these with you on the formula sheet. So consumer surplus is the integral from 0 to q of your demand function minus p times q. Okay? Remind me, what does P, what does Q represent? What do these letters represent? P and Q. Price and quantity. So in our case, what's P? 9. What's Q? 1. So 0 to 1. And then my demand equation, of course, is just 1, or no. Sorry. X minus 4 squared dx minus P is 9, X is 1. So 9 times 1 over there. Or Q is 1. Awesome. How do I integrate X minus 4 squared? How do I integrate that?
Is that by partition? Do you use by substitution?
Oh, you could use substitution. You could use substitution because, heck, let's do this by substitution. Do you have to? No, I could also just, in fact, so that I don't have to worry about bounds, I can just multiply the X minus 4 out again. And do it that way.
Oh.
Okay. But if you're very comfortable with substitution, go for it. Do it by substitution.
I'm gonna do it the second
Yeah.
way.
There you go. Nice. Okay. Minus 9. Now I'm using fundamental theorem of calculus, so I'll go ahead and find my antiderivative. I get 1/3 x cubed minus 8 times 1/2 x squared plus 16 times x, evaluated from 0 to 1. And then, of course, I still have this minus 9. When I plug in 1, I get 1/3 minus 8 times 1/2 is 4. But when I plug in 1 squared, what do I get? Still just 1 plus 16 times 1 is 16. What happens when I plug in 0? You just get 0. So that's as far, or that's all I need to do there. I get, and then of course, so minus 0, I'll put that there. So there's my upper bound, there's my lower bound, and then I still have this minus 9, and you end up with 10/3, which is $3.33. That's the consumer surplus. So that's kind of the numerical value of how much the consumers feel like they saved. Supplier demand, very, very similar process. You just flip the equation, so you end up with 9 times 1 minus your integral from 0 to 1. And instead of integrating your demand curve, you're integrating your supply curve. Awesome. Which I think if you do that one right, you should get about 1.67. And that's how much the suppliers feel like they profit out of it. Cool. Questions about equilibrium? Or questions about consumer surplus, supplier surplus, producer surplus? Okay. Moving on then. How are we doing? We still got 30 minutes to get through 9 more problems. Oh, I gotta kick into gear here. Okay. Next, we get into 5.2, which was if you have a constant income stream, right? What's your present value? What's your future value if you have a continuous income stream? So this is the problem where we want my future value. A lot of times we use A for future value. We want my future value after 18, well, no, in my case it was, my future value after 18 years to equal 280,000. The interest rate is 5.6%. First off, it asked me, okay, how much would I need to invest now? What's my present value if I want my future value to be 280,000? We've already talked about this, right? We covered this already. So P naught is just going to equal my 280,000 times E to the negative 0.056 times 18. Why negative again?
Because you're equaling it to P naught.
Right, because this is my future value, and I'm solving for present value. Because I'm working backwards, that's why I need a negative in my exponent. Very nice. This should give you, let's see, in case you guys are curious, this gives you about $102,185.48. B says, okay, well, what would your continuous money stream have to be in order to get this future value? Instead of doing one lump sum, how much would you need to contribute every single year in order to end up with this same future value? Well, in that case, I can use my future value formula for a continuous income stream where it's A equals R over little r times e to the RT minus 1. What do I plug in for A? 280, right? That future value that we want. We want to end up with 280,000. What do we plug in for R? Big R, sorry, capital R. What do we plug in for capital R?
Your income.
Which we don't know that yet, right? This represents my continuous income stream, which that's what we're solving for. So R is what we're solving for. What do we plug in for little r? I think on your formula sheet, I really should switch this because on your formula sheet, they use K. But it represents the same thing. It represents your interest rate. What do I plug in for K? 0.056. And then this is multiplied by E to the 0.056 times 18 minus 1. And then you can solve. Solve for R. And you should end up with $9,010.90. Okay. Very nice. Any questions about continuous income streams? Okay. So that was something that we talked about, 5.2. Number 21 is another problem about the same kind of thing. So this is talking about world reserves of natural gas, and guess what? This is still considered a continuous income stream problem. We're going to see why. So in the year 2006, so that's important, 2006 is going to represent T equals 0. Okay? In the year 2006, the world reserves of natural gas were approximately 8,015 trillion cubic feet. What is that number going to be? The principal. It's your present value. It's what you're starting with. So this is, I can go ahead and mark that as P naught, or we also use the letter B for present value. Okay? In that same year, the world consumption of natural gas was approximately 102.6 trillion cubic feet and was growing exponentially at about, oh, let's see, I'm reading the wrong numbers. Oh, goodness, I'm doing this again. Okay, got that. So at the beginning, the rate at which it was changing was 110.1. Okay.
Wait, that's the rate it was changing, or the rate it was at that year?
That's the rate it was at, and this word is kind of, or this problem is kind of worded weirdly, and then let's see. Yes, and then the rate at which you're pulling. The rate at which we're consuming natural gas is also growing. It's growing by 1.9% each year. Okay. Now, don't be confused, because when I initially read this, I was like, oh, does that mean we're going to have to create this weird exponential formula for like what our what our continuous stream is. But the way we can interpret this is, how am I going to interpret this 1.9%?
Okay.
Yeah, that's your K. That's your K. Okay? And how do we interpret 102.6? Or sorry, 110.1. I keep messing this up. How do we interpret this 110.1?
Is that the capital R?
That's your capital R. Right, exactly. So I'm going to interpret this as my capital R. It's how much you're pulling out each month. And yes, and this is where it gets a little confusing, because you might be thinking, but that's changing. Well, we're taking that into account by just using the rate of 1.9%. We're taking that into account by using the 1.9%. The world consumption. Yes. Okay, so in that case, how do I set this problem up? How do I set this problem up? Yeah.
0 is equal to 110.1 over 0.019 times e to the 0.019 times t.
Times t. Why? Notice, yeah, you just put in t. Because do we know how long it takes? That's exactly what we're solving for. It says, in what year will the world reserves of this resource be depleted? So, I don't know how many years it's going to take. That's what I'm solving for. But notice how you use the future value equation, right? Use the future value equation, which is fine. And we might be thinking, oh yeah, I want my future value to be 0. The problem with this is future value, the way this future value and present value equations are set up, or at least the future value equation, the way it's set up is it's going to assume growth. It's going to assume it's growing. So this number's only going to get bigger. If I try and solve for this, it's going to be impossible. Because if my function's growing, there's no way I can end up at 0 when I'm done. So instead, how could I change this?
Negative K.
Ooh, I could maybe treat this as a present value equation, maybe? Okay. Honestly, though, we really just need to flip how we're thinking about this. I can still use this equation. I can still use this setup, but instead of setting it equal to 0, I'm going to set it equal to 8,015. Why? Because if we write it this way, then how we're interpreting this is this measures my consumption, my total consumption, right? Because that's what this represents. That represents your consumption per year, and then this represents how that consumption's growing, right?
So once the consumption matches.
Yep. So since this is measuring total consumption, we want to figure out where the total consumption matches the amount that we have. And then solve for that way. Everybody okay with that? We want to see where total consumption matches the amount that we still have left. Okay. And then, so if you do it right, you'll end up with t equals 38.088. So in about 38 years, where's my starting point again? 2006. So what's 38 years after 2006? 2044. Okay, we're really close. I'm not sure if these numbers are accurate in any way, but yeah.
How would you even take the t out of the exponent to solve for it?
Oh, great question. We've already talked about this a little bit earlier, right? I can't remember. It was one of these chapter 3 problems where, yeah, right here with that doctor problem. When will 90% of doctors prescribe the medication? we had this same situation where we set it equal to something and we were solving for t. We eventually get to this point where, how do we get that t out of the exponent? We take the natural log of both sides.
Oh, okay.
So that's how you're going to do it with this one too. Once you get to that point where you need to get t out of the exponent, take the natural log of both sides. Awesome. But very perceptive, because you will have to do that with this problem. Okay, I really need to speed up here. Let's see, what are we on? 24? On 24? Uh-oh. Come back! Oh, we're on 23?
22.
Where did this? Oh, yeah, right. We're only on 22. Huh? We're only on 22. But where did this go? Oh, yeah, there it is. Come back. I can't afford to just waste this time here. I was really hoping we were on 24 because that would mean I had much less to do. But, okay. 22. 22 is, well, how do I do this if I have a perpetual income stream? So what do I do if I let my continuous income stream of $3,400 be perpetual? Meaning I'm just going to let it keep going for forever and ever. Okay. Well, remember, we had a nice, simple formula for this as long as I'm calculating present value. Can I calculate future value? No, not if I'm letting it perpetually happen, because then there's no end date, right? So you can't calculate future value if it's perpetual, but you can calculate accumulated present value. How did this one work? If you write the whole formula, you have this 1 minus e to the negative kt. But what happens to this term if I let t get infinitely large? It goes to 0, right? This term will just go to 0, leaving you with just r over k. So for this problem, it's just 3,400, and then I didn't actually tell you the interest rate. The interest rate is 6%, so 3,400 over 0.06. And that gives you your accumulated present value if you let it keep going perpetually. Oh yeah, that was a good one to make up time. 23. Okay. Aha. 23 is my probability density functions. So 5.4, talking about probability density functions. It gives me a function. It gives me the function 1 over 50x, and this is the probability that a dart lands on a number line. And it's always landing in the interval from 0 to 10. Find the probability that the dart lands between 8 and 9. Okay, that's what you're finding. You're finding the probability that the dart lands somewhere between 8 and 9. How do I do this? Integrate it, right. You integrate between those values. Integrate what? You just integrate your probability density function. That's exactly right. So that's how probability density functions work, is to find a probability for a certain interval, you just integrate over that interval. Everybody okay with that? My antiderivative is just 1 over 100 x squared. Integrate that between 8 and 9, and you should end up with about 0.36. Notice how that value's in between 0 and 1, because what does it represent? A 36% chance. Very nice. Okay, moving on. 24 is when we start getting into chapter 6 stuff. So everything else is chapter 6. Okay. 24 gives me a multivariable function, f x y z is equal to 5x, minus 8y squared plus 9z cubed minus 6. And then it asks me to find, what is f of 6, negative 4, 1? What does that mean I'm doing?
Just plugging it all in.
Plugging it all in. Be specific. I'm plugging 6 in for x, plugging -4 in for y, and plugging 1 in for z. So 5 times 6 minus 8 times -4 squared plus 9 times 1 cubed minus 6. Awesome. Any questions about this one? Pretty straightforward. Hopefully that one's on the test, right?
Is it?
I don't know. Okay, 25. Actually, I do know, but I'm not telling.
Isn't there like a pool of problems, like pulls like 20 of them or so from the pool of problems?
Yep.
Okay.
But it's not random. It is fixed. So
Oh.
I do know which ones are on the test. But. Okay. Domain. So 25 is all about domain. So here's my multivariable function. F of x, y is equal to 8 times the square root of 7 plus x squared minus y. And it wants me to find the domain of this function. Well, why is domain important for this problem?
Because you root.
I have a root. I have a square root, which means what has to be true about everything under the square root? It has to be, oops, sorry, that's 7 plus x squared. Sorry. 7 plus x squared minus y. It just can't be negative. It can equal 0, that's fine. It just can't be negative. So I'm going to say this has to be greater than or equal to 0. What do I do with this?
So for either x or y.
Solve for either x or y. Which one's probably going to be easier? Solve for y. And in fact, your multiple choice only has it solved for y. So that's another way you can tell. This one's multiple choice. So if I solve for y, I'm going to go ahead and add y to both sides. Makes it nice and easy. I get 7 plus x squared must be greater than or equal to y. If I wanted to switch that around and put y on this side and 7 plus x squared on the other side, what would I have to do with my inequality? Also flip it. Okay. So there you go. So y just has to be less than or equal to, oh, why did they, oh, yeah. Y just has to be less than or equal to 7 plus x squared. Very nice. 26. Now we get into partial derivatives. Okay. So 26, we have a multivariable function. That is the square root of x squared plus y squared. And I want my partial derivatives. Okay. So how do partial derivatives work again? Partial derivatives represent me taking the derivative in terms of just one of the variables. So f sub x means I'm going to take the derivative of this function in terms of x. How do I treat y? As a constant. I'm going to treat y as if it's not changing. So if you wanted to help you out, if I wanted to, I could like write a big 5 over this or something, right? I could write something over it to just show I'm just going to treat this as a constant. What does this derivative require? Chain rule, right? I do have a function inside of a square root function. So this is the same thing as x squared plus y squared to the 1/2. So I'm going to use chain rule here. I get 1/2 x squared plus y squared to the -1/2. That's me taking the derivative of the outside function. You keep the inside function the same. And then what's the derivative of the inside function?
4x is going to be 2x.
2x
Y is going to be 2y.
plus, how is y squared changing if x changes? It's not. It's not changing, right? Because we're treating that as a constant. What's the derivative of a constant?
Zero.
Just 0. So that's it. My derivative of the inside function is just 2x. When I do my partial derivative in terms of y, guess what? It's like almost exactly the same, except when I take the derivative of the inside function, if I take it in terms of y, what do I get?
2y.
2y. Right. Ready? Okay, any questions on this one? Oh, and then, sorry.
So they won't want us to simplify that. That was.
Yeah, you don't need to simplify it.
Okay.
Yep. You don't need to simplify. Yep. So that would be just fine. And then I think later in that problem it does have you plug numbers in, but if you know how to do 24, then you should be just fine with the second part of the problem. Okay, 27. Okay, we've looked at this problem before in class, but this is the one where you've got your productivity if you have specific units of labor and capital. So in this case, X is units of labor. And we talked about what that means. That could be like number of workers. And Y is units of capital, which is like dollars. Okay. Oh, good thing we're almost done. Okay. Part A is find the number of units produced with 35 units of labor and 1,135 units of capital. That's just me plugging those values in, right? Plug in 35 for X and plug in 1,000. Oh, dang, I'm doing this again. Oh. Use the numbers from down here. 25 units of capital. No, sorry, 25 units of labor and 1,056 units of capital. Okay. Right, all that's saying is just plug those numbers in for X and Y and see what you get. So in my case, I get 105, 710. So that's how many units I'm producing. Okay. Then, part B asks you to find your partial derivatives. So P sub X, P sub Y. P sub X, how am I treating Y? So, because this is being multiplied, it's not that it's going to go to 0. Because it's being multiplied by your X function, you can just ignore it, just like how we ignore the 2,000, right? If I were to take the derivative of this, I can ignore the 2,000 and take the derivative of everything else. So the same thing. I'm going to ignore the 2,000 and the Y to the 1/5. Oh, sorry. Back to Y. I can ignore the 2,000 and the Y to the 1/5 and just take the derivative of this piece. What's my derivative? 4/5 X to the negative 1/5. And then I can simplify that by just multiplying my 22,000 and 4/5. And I get 1,600 X to the negative 1/5, Y to the 1/5. You know, I do switch order around a lot, but remember, with multiplication, order doesn't matter. You can do it whatever order you want. Okay. Okay. P sub Y, I'm going to do something similar. I'm going to ignore the X to the 4/5. I'm going to ignore the 2,000 and just take the derivative of Y to the 1/5. So, I'm ignoring those. Take the derivative of Y to the 1/5. I get 1/5 Y to the negative 4/5. Now I can multiply the things together and I get 400 X to the 4/5 Y to the negative 4/5. And there's my partial derivatives. And the rest of the problem, part C, is just, okay, evaluate it for 25 units of labor and 1,056 units of capital. Okay. So P sub X, 25, then plug in 25 for X and 1,056 for Y, and you get 3383. And then P sub Y, 25, 1,056, you get 20. So if I plug in those values into my partial derivatives, this is what I get. What do these numbers actually mean? What does the 3,383 mean? First of all, it's a derivative value. So what does that mean? It's a rate of change. It's somehow a rate of change. So this represents a rate of change, but a rate of change of what? Well, units of labor is my independent variable, right?
Units of capital.
And units of capital, what are we assuming about the units of capital for this partial derivative? So I'm just focusing on this one for now, right? Let's just focus on this one for now. What's changing? What's my dependent variable?
That's the X, which is, I don't remember.
No, X is one of my independents. What's my dependent? P, which represented the amount of items I'm producing. That's my dependent. P represents the number of items I'm producing. So let's go back to 3,383. What does it represent?
Change in units.
Change in units produced if I change the X value by 1, which in our case is units of capital, right? No, sorry, man.
X is labor.
Units of labor, right? Units of labor. So, 3,383 more units produced if what?
Like increasing labor by 1.
If I increase the units of labor by 1. And this is, of course, assuming that I'm starting at 25, right? Because what did we plug in for X? We plugged in 25 for X. So if I hire the 26th employee. Does that make sense? Right? I already have 25 employees. If I hire one more, this is how many more units I'm going to be able to produce. What are we assuming about the units of capital? It's staying fixed at what?
1056.
1,056, right? Capital is fixed at 1,056. And I think we've talked about how that can be interpreted as money. So that's exactly what this value represents. If we look at the other number, if we look at 20, 20 is the exact opposite. 20 is how many more units will I produce if I'm going to produce 20 more units if
1 more unit of capital.
if I devote one more unit of capital to this production, right? If I spend one more dollar, if I spend $1,057 instead of $1,056. If I spend one more dollar, what are we assuming about the number of employees? It's fixed, but we're fixing the number of employees at 25. Okay, one more. We have one more minute for question number 28, our last one. Okay. This is maximizing profit. This is that optimization idea. Okay. And luckily we did this the most recently because this is what we did last Monday. This is 6.3. Okay. If I want to optimize profit and I give you a revenue equation and a cost equation, first off, what are you going to have to do? Yeah, create the profit equation. How?
You subtract.
Right, you do revenue minus cost. Okay? So first of all, you need to make the profit equation. And then how does optimization work with multiple variables? With a multivariable function? You guys remember? How does optimization work?
You got 2y squared.
That is 7y squared. Sorry. I mean, the numbers aren't going to matter too much because we're not going to have time to actually come up with answers here. So I just wanted to kind of go through the process. What's my process? Well, normally with optimization, it's just you take the derivative set equals 0. But this is multivariable. So I have two derivatives. I have the partial in terms of y and the partial in terms of x. What do I want to be true about both of these?
I have to take the second derivative.
I want both to equal 0. We're not there yet. I want both to equal 0 in order to get me my critical points. So I'm going to take the partial derivative of my profit equation for both partial derivatives, set both of them equal to 0 in order to get my critical points. So for this problem, I think you end up with, what's my 4,3. You end up with a critical point of 4,3. And then remember, we had that process for deciding whether it was a min or a max, where it was like you take your f sub xx times f sub yy minus your mixed partial squared, and then you decide whether that, and then you figure out if that's greater than 0, less than 0, or equal to 0, in order to figure out whether it's a minimum or a maximum. Okay. Sorry, we ran out of time for that one, so couldn't quite go through it as thoroughly as maybe you wanted. But if you have questions on this one, just feel free to ask me. Awesome. Okay. This is it. I guess I can stop the recording.